Hi, so I'm Matt. I'm going to talk to you a little bit about Go and microservices, and I guess other buzzwords. Yeah. So a little quick intro. Well, one, thank you very much for coming. I guess you're missing Troy's talk, so yeah, that means a lot. I'm Matt. I'm on Twitter here, so if you have any questions, I'll be around all day. Otherwise, give me a shout on Twitter. And I work for a company called Monzo. So has anyone heard of Monzo? Yes. OK. So I actually did a talk at NDC 2 years ago on handling failure in microservice architectures, which was perhaps a little premature, as we hadn't really launched a product at that point. Thankfully now we have launched a product, and a few more people have heard of us. So maybe this will be slightly more relevant now. So to give you a little bit of intro, if you haven't heard of Monzo, we give out these kind of luminous debit cards. However, that's like a kind of side part of what we do. Our mission really is to change the way that people interact with finance. And for me, that's kind of a personal thing. I found it's very difficult to kind of easily get spending data about like what your expenditures are, easily keep track of your money. That's not something that banks have traditionally made particularly easy, although that is hopefully changing very soon with open banking. But that's kind of always been something that I personally have really had an interest in, like having better control of my finances and having ideally someone who can tell me to like spend less on one thing or put my money over here, and that can kind of help me kind of live a better life, really. And the flip side of that is that banks, to me, are a bit like this. So banks are quite dated. You often have to go into a branch to do something. Sometimes you have to go into a branch and the person in the branch can't help you, and they direct you to a phone in the branch where you then phone someone. And none of this is a particularly good user experience. Like if we were focusing on UX for a second, banking is not that area. Like banking is generally terrible. There are a very small, notable couple of exceptions. However, as an industry, banking probably has some of the worst user experience of all areas. And that's a problem because you really can't function in the modern world without a bank account. It's quite difficult, especially if you move countries and then you can't get a bank account. And that's really difficult if you actually need to pay your rent or even get a house because you have no way of proving to most of these kind of companies that you're a real person. So banking is kind of core to everyone's life, and it's something that has terrible user experience. And that's something that at Monzo we want to change. So we started quite a while ago, back in February 2015. Turns out building a bank takes a really long time. I don't know if anyone would have guessed that. It took a lot longer than we thought. And to help us speed our way along this kind of journey, we realized we wouldn't be able to give people what you would consider a traditional current account for quite a while. We'd need a full banking license to hold funds, and that's not something you can easily get for a lot of very good reasons. So in our case, we launched a prepaid debit card, and this is this neon card that a lot of people have seen. And then slowly over time, we've built up the kind of banking expertise and the technology behind that so that we can add the features you'd expect of a normal bank account, and then kind of from that point, start iterating. And that's kind of the point we've got to now. We're actually a little bit off the side of this picture. We have run through a kind of an alpha stage, a beta stage. We gave out a few 100,000 cards. We've now started upgrading people to full current accounts, which gives you all the extra kind of features. And that's kind of where we are now, which is really kind of fun for me because it's taken pretty much 3 years to get to that point. And now we can do all the really cool things that we thought we'd be able to do a long time ago. So to give you a little bit of context, we give people kind of an app. All your interaction with us is through the app. We have 24/7 chat. That means we have teams around the world, so they don't have to stay up all night. And we give people a debit card so they can control their money. And in the app, you can do really basic things like see where you spent. You actually see like a description of that shop, which makes it a bit easier to control your money. We categorize those automatically. You can do things like searching. which most banks you can't do. You can actually search for emoji, which is obviously a really important feature. So if you do ever want to search for the coffee cup, that does actually work, and it will pull out all of the coffee-related shops. You can also store things like receipts and stuff. So if you have expenses, you can actually pull those out really easily and build like an expense report. I store pictures of my brunch, just as a kind of memories of where I've been. And other really basic things like you can freeze your card if you lose it, and crucially, if you find it 2 minutes later, you can unfreeze it. And I think this is a feature we kind of mention quite a lot, but I think specifically at developer conferences, this is a really interesting one. Why doesn't everyone do this? It's literally a bool flag in our database of whether your card is enabled or not. I mean, seriously, it's actually an enum. There's like 4 different states. But like, this is the first feature we ever added. Like, okay, we have cards. We put a card in the machine. That means we get an API call in real time every time you charge your card. We've since built our own MasterCard processor. But as a prototype, we used a third-party card processing system. So yeah, we look your card up in the database. It's not enabled, decline. Literally that simple. And it turns out if you re-enable it, we can undo that. So this is one of the like really small UX things that is trivial. And all large companies, like all large banks, have loads of people who are really intelligent, who have really simple ideas like this, but like actually building them is a slightly different problem. Yeah, this took like 10 minutes to build. So to go all the way back, if you were considering building a bank, at some point you're going to be staring at this screen, which is problematic, kind of like intense terror. Because like, how do you really start? Any large software project, like where do you start right at the beginning? You can spend ages designing how everything will work. Ultimately, you probably don't really know how it will work in the end. At this point, I basically knew nothing about banking, so now I know slightly more about banking. And that means really that all assumptions you're going to make at the beginning of a project are probably wrong. So there were a few decisions we needed to make right up front. And one of those was like how we could just get going really quickly and build something. So in our case, we chose to use Go as our main language. Not our only language, but as our main language that we would knock out a prototype in and then kind of iterate on from that point. So has anyone used Go or seen the Go Gopher? Cool, a few people. So I guess the real question is, why would we use a relatively obscure language to build something that potentially might store huge amounts of people's money, and we might need to bring lots of people on if our team grew? And there's a few reasons for that. We could have used any language, really. Like, you can build anything in any language, and I wouldn't say that any is any better than any others. So this is not one of those talks. This is not a talk to say you should all ditch everything you're doing and use Go. That's not the case. Go is good at certain things, but not everything. And in this kind of talk, I'll mention what those kind of pros and cons are. So in our case, I'd say the real kind of sum up is that it's very simple, it's an effective language to build things in, and it is very scalable. And I mean scalable in a number of different ways. So to go through those, the language itself is extremely simple. I've been programming probably full-time in Go for about 5 years now, which I found a great experience. And before then, I programmed in a number of other languages. And usually in those other languages, you can do really, really clever things. So you can write an extremely small amount of code that's kind of magical, and it's like, feels really good. And the problem is, if you ever need to debug that, it takes a really long time. You have to like start stepping through into frameworks that you maybe haven't written, you don't understand, and that takes a really long time. And that is not the kind of Go way of doing things. There are lots of tools and packages that you can use. However, Go, you write extremely simple, quite boring code. It's quite boring. Like, just write lots of code. It's very straightforward. And that's a really good thing, because it means if you haven't written that code, you can go and read someone else's code, and you can understand it. And that's a massive benefit. The language itself is very simple. There are a relatively small number of constructs. The The type system is quite simple, so it's statically typed, and it's not as expressive as a number of other languages. As an example, you don't have generics, which is a kind of point that people keep on bringing up in the Go community. And there are definite disadvantages to not having constructs like generics in your programming language. You have to write the same thing several times. However, sometimes you can solve it without being really generic, and you can have a really simple solution. And sometimes you need to write a bit more code, but it is still really simple. So for us, as we've grown our code base, I found this a massive benefit. I can go to any area that I didn't write, and obviously there are slightly different code styles. Go has a tool that you run called Go Format, which will format all of your code into the specified kind of language format. So as an example, there are no tabs versus spaces arguments here. That's not an option. It's tabs all the way. And lots of other things like that. You run a tool every time, and it means your code is consistent across your entire code base. So there are some style variations, but the main code is extremely readable. The other advantages are kind of, which I guess is the main touted advantage in the library, are things like lightweight concurrency. So I've got a few examples of this, but although you can write extremely simple code, Go makes it very easy to run that code concurrently. And that means you can write really quite complex applications that are highly concurrent, which is particularly good for web services, which I'll come on to in a bit. And because of that, having concurrency as like a first-class citizen of the language makes it really awesome to do. So in a lot of languages, if you want concurrency, you have to spin up threads. In Go, we use things called Go routines, which are essentially lightweight coroutines that can be moved between threads. And in a traditional application, you would have tens, hundreds of thousands, potentially millions of Go routines. And that's actually normal. They're extremely lightweight. So if you want to fire up a new Go routine, you pretty much, I think it allocates 8K on the stack, and that's it. And to use that in your code base, you would literally have some function that you would execute, and it will block. And if you want to make that execute concurrently, you would literally write the keyword go and a space before it. And now it will execute concurrently with its parent. Now, that's great. Making concurrency this easy is an incredible kind of positive experience for the language. However, anyone who's debugged concurrent applications probably immediately realizes how easy it is to really shoot yourself in the foot here. You can make things extremely complicated. You can have loads of things that are running concurrently and might be changing state everywhere, and that might be a really bad thing. So although it is easy to do, there has to be some element of responsibility here. But it means you can design programs in a slightly different way. So to use our example, we have, in Go, you always have a main package. That's like the root of your program. You have a function main, which is, again, the root function of your whole program. And then somewhere inside this function, we're going to call handle request, and we're going to run that in a Go routine, so it'll execute concurrently. What that means is the program flow will run through here, and then we'll get to this point, and we will fire a separate Go routine, handle request, which will now execute concurrently with the main Go routine. And to be clear, the main program is itself running in a Go routine. So you can do any number of these. Crucially, when main gets to the end here, it will actually exit. So if your handle request hasn't finished by that point, it would exit. So in a lot of programs, you might fire lots of things, and then you'll use some synchronization mechanism to wait for those to exit, and then you'll clean up and exit the program. So as I mentioned, Go routines themselves are extremely lightweight. You can fire them very, very quickly. When you are literally firing one of them, you're allocating 8K memory on the stack. That has slowly increased as the Go scheduler is improved. And that means that, they're like pretty much instant. So when you're doing this, you now have the opportunity to modify huge numbers of variables across your application concurrently at the same time. which is probably a bad thing. So one of the kind of main points I'd say, there's loads of documentation on the Go website. One of the really good articles is called Effective Go. And that is like the step on from a style guide. It's like the ethos behind how you should program in Go and lots of examples of specific syntax and kind of constructs. And one of them is this. So you shouldn't communicate by sharing memory. Instead, you should share memory by communicating. And this is a very kind of core concept in Go as a language. You can have many variables in memory, and if you have a reference to them, you can modify them from any number of Go routines. That's obviously bad, because you may have things which are modified in and out of order, and the Go scheduler may reorder the execution of your Go routines. So you have concurrent access on things like maps and arrays and various other things. And mutating those concurrently is generally a bad thing. Go will usually panic if you modify these things concurrently. So what this sentence is trying to tell you is, instead of like having references to specific variables and mutating them, we should instead pass those things around between Go routines. And Go has, again, a primary kind of top-level construct called a channel, which allows us to do this. So these two concepts, the Go routines and channels, are the way that we build all programs really in Go. And these are just a way to send a message from one Go routine to another Go routine. And that is straight through. You could send pointers. Probably don't do that unless you know what you're doing. So this allows us to have many concurrent running sections of our code, and then we can move our different messages between them and communicate in that way. So that means we can construct things like pipelines. We can have one Go routine that's doing one particular operation, it passes the result on to another one, passes the result on to another one. We can also do things like fanning in and out. So if we have many Go routines that are generating particular results, we can then pass those into one thing which can aggregate them. And this gives us ordering. So we have one synchronous operation, which we're reading in from many results from a channel. So we get synchronization across our program. The other one is if we have a large pool of things we need to process, we can spin up many Go routines that listen on one channel, and that means we can effectively load balance work across a large number of discrete Go routines within our application. So those kind of things allow us to do quite interesting things within our application. And then by using those, we can construct like the application as a whole. So digging a little bit deeper into that, Go routines themselves, I mentioned, are really lightweight. And you can spin up loads of them really quickly because they don't do any, they don't run as OS level threads. So the Go scheduler has changed quite a lot over the last couple of years and is now incredibly efficient. So usually in most languages, your kind of performance bottlenecks will come from spinning up new threads for concurrency. And that means you have context switching, you're moving memory in and out of cache lines and CPUs. So in Go, the Go scheduler the runtime will spin up one thread per core, and then it will multiplex all of your Go routines across those without you really knowing anything about it. And that means that you don't have any context switching at that point. As soon as one of those threads blocks for like I/O or to read disk or memory, it will park that, spin up a new one on the core, and then move other Go routines which need to be scheduled onto that. So it will do that incredibly efficiently, and that's why you can run like potentially millions of Go routines in one process. Also, Go is a memory managed language. So a long time ago, it had kind of a stop the world garbage collection. Thankfully, that has gone away now, and it has a really efficient concurrent garbage collection. So you can generate huge amounts of garbage, and the runtime will just deal with that for you. So that means, like, if you have come from, say, another language like Ruby or Python or, heaven forbid, PHP, which I used to do, you don't have to deal with those kind of things, and moving to like a compiled language or something like Java is quite difficult. You have to change your mindset quite a lot because you need to keep track of all of these things. And Go is going to do that for you, so that's really straightforward. It's extremely efficient at that. The other thing, if you're using this as a large company, is the language stability. So Go is about to upgrade to version 1.10. All subversions of the Go 1 language have had a compatibility guarantee. So basically, if you wrote a Go 1.1 program and now on 1.10, it should still compile. There's been lots of performance changes under the hood. As I mentioned, the memory management, and specifically the garbage collection, has pretty much increased several orders of magnitude over that time. However, you can just recompile your program, and it's basically fine. That's kind of a guarantee that the Go authors provide. And that means if you're using this in a much larger company, you can upgrade versions and get performance increases for free without having to schedule like loads of development time to rebuild and re-update to a new language version, which is pretty awesome. So popping all of that together, at Monzo, we've been able to switch to using Go. We started using it pretty much from the beginning. We've got a really simple language, which means that it's easy for people to join our company and start using. We can pretty much rely on the runtime to deal with all of these things for us. And we can, rather than focusing on the language level problems, we can focus on building our actual product, which is the interesting part. However, what we don't want to do is build one giant application if we're building a bank. So I guess I have to mention the term microservices, which in our case, like, it's extremely hypey, and that's something that a lot of people talk about, very specific things about microservices. What we mean when we say microservices is just really small applications. They're really simple. They're just HTTP servers. That's all we're doing. There's no like special inferred meaning from this term. And the reason we use Go for this is because it has extremely low overheads. So the average memory usage of one of our binaries will be like 40 megabytes. And if we compare that to like one of our services that's running the JVM, that's hundreds of megabytes. It means we can deploy a lot of these, and they're really efficient. Deployment is really simple as well. So Go is statically linked, and that means you can compile your entire code base into a single binary. You have one file. That is executable. You put that on a Linux server, and you execute it. And that's it. That's your deployment. You can do really complicated things if you want, but the binary itself contains the runtime, it contains all the dependencies, and it's literally executable. So if you want to do anything with deployment, you don't have to deal with like environments and working out which version of the runtime you have built into your Docker container, for example. You don't have to make sure you've got all of the files with it. You literally compile it, and then you run it. And that's like amazing for a development team. So if you wanted to get started with those, there's a few options. So if anyone's seen GoKit, this is a kind of standard library for microservices. And this will do things like let you create a server. It'll handle all of the request flow for you. And then you can just pretty much build really simple functions, which it will run. GoKit is quite like pared back. It lets you specify kind of all of the extra things yourselves. Whereas if you want something that's kind of more fully featured, then something like Micro, which is kind of a fully comprehensive toolkit, really, this is probably the one you want. So with Micro, you can literally define a function. You can run that, compile that as a binary. You'll now have a HTTP server. It supports a number of other transports as well. And then you can deploy that. And it comes with like lots of kind of stubbed out things for observability, server discovery, and everything that I'll come on to in a bit. We have our own Typhon. Maybe don't use that, but if you want to have a look on like how we build really simple applications, this is like really straightforward. And in our example, literally when we build a service, it's a function that takes a request and returns a response. It's really that simple. We then usually put some of the related ones together so they can share some of their domain logic, in which case we will register a number of them with paths and then register specific handlers. So this is just like any normal web application. You're registering a specific routing path, and then you're executing a function, which is literally going to take a request and return a response. And it's really that simple. as of 2 days ago, Amazon now support Go on Lambda. So this is a good example, again, of how the overheads are so low, you can actually run them as Lambda functions. And building them is really easy. You can test them locally because you can compile them against the toolkit, and it just runs it locally. So there's a post on the Amazon blog. Check that out if you want to just kind of play with Go in Lambda. And again, this is really simple. So if you want to do this, you are going to define, again, a function. And this is like there's a bit going on here. So you're going to take a function, and this first parameter is going to bring in an API gateway proxy request. So has anyone used API gateway on AWS before? Okay, a couple of people. So API gateway allows you to define like a route to execute a function. And this is just going to take that request. You're going to do something with it, and then you need to return a response and an error. And in Go, you can return multiple parameters from your functions. It allows multiple return parameters. And the kind of common convention is if you have an error, the last parameter is the error. So this is just that kind of like standard way of doing things in Go. The actual function main here is literally lambda start my function. So that's it. So if you want to have a play with that, there's loads of details on the Amazon blog. It's really, really straightforward. You pretty much write some code, compile it, and push a zip to Amazon, and it will execute it, which is kind of awesome. So that's all well and good. At Monzo, we started deciding we would use Go for all of those kind of reasons. And that brings us like all the way back to the beginning. How do you build a bank if you are starting from scratch? And you know that it's going to be really hard. I think like that's the one thing we did know right at the beginning. Building like a large complex application is generally quite hard. Building one that stores people's money and has to be really responsible is quite terrifying, to be honest. So at the beginning, we were pretty much like this. We're going to have a mobile app. That's a solid decision. You can get behind that. And then that is going to do something. And then, yeah, that'll store your money. Great. So obviously, we're going to have some form of server-side application. And right at the beginning, we knew that that was going to get complicated. We'd have probably a database behind that, maybe multiple databases. The application's going to get larger over time. We'll need to add all sorts of things in, like emoji-based search, and like probably caching, and like lots of other crazy features that banks require. And this is a really common thing that everyone finds themselves in. It's a really common story. You hear from lots of large companies. You build a really big application, and unsurprisingly, it's really hard to develop on. Deploying slow, you have one code base everyone's contributing in, et cetera, et cetera. And these are the reasons that people have talked so much about microservices over the last 4 or 5 years, and why people have started breaking their applications into much smaller chunks. And that's exactly what we did right from the beginning. So we started off with a kind of large number of discrete applications that all did one thing well. They have a very bounded context. And that means that you can focus on how one of these works without needing to really know about the whole application. All of these are maintaining their own APIs. So you effectively have API contracts between each service. And in our case, we communicate via a number of ways, either synchronous kind of RPC-based calls, which we require for latency-sensitive request response. And we also use a lot of queues and do a lot of like event sourcing kind of things, which allows us to push those into queues. And if we have problems, we can kind of slow down our processing and deal with that and bring things back up. In our case, we started off in, I mentioned, February 2015, and we slowly added more and more services. And I think the thing to bear in mind is if you start that way, especially if you're starting at a startup where you don't have an established product, you probably don't know how your product will work. And that means that it's very difficult to know what this does. You'll make some guesses, and you'll build an API. And a good example of this is how we built our transaction API originally. We thought we read some stuff, like this is how transactions in the real world work. And I mean like kind of monetary transactions rather than transactions in a specific database terminology. And inevitably, those assumptions were wrong. And that meant that we had to rebuild lots of these things and change the APIs between them, which is quite painful. So if you're starting off right at the beginning, this is a problem. And this is why most people build an application, a prototype quickly, and then at some point in the future, you pull out specific sections which are performance sensitive. So in our case, we started right at the beginning, and we've slowly added more and more services and deleted a few in the middle, and we're now running about 415 services. And these are discrete services. Each one of those we're running many copies of based on performance requirements. So ultimately, we have sacrificed the individual simplicity of these for like overall complexity of our system. But those are things we can manage. So to go all the way back, we started off with an app that is going to connect to some form of API, and we need to deploy that on a server somewhere. We could use kind of Lambda or some other like serverless products. I'm not sure those were like particularly well used when we started. But in our case, we have a server that we need to run something on. And inevitably over time, we're going to add more of those. And we end up in another problem where as a small development team, we've now turned ourselves entirely into an ops team where we just have to manage servers all the time, which is again problematic. So to solve this problem, we switched to using Kubernetes. And Kubernetes, if anyone's used, allows you to kind of run a platform across all of your services and essentially stick that as like one block of compute power, one set of resources that you can scale independently, and then on top of that, you can run all of your applications. So we can run a kubelet on each one of these servers, and that will decide, that the scheduler will decide in the Kubernetes master which applications are going to run on which servers, and then the kubelet will execute those. And most of the time, we're running these in Docker containers, so the kubelet will essentially pull the Docker container and execute it. Behind this, you have etcd. So this is our consistent data storage, and this is what Kubernetes uses to store all of its data. So one thing very important to know, if you are going to use Kubernetes, it is extremely important that this is stable and reliable. If your etcd cluster breaks, then everything will break completely. Nothing will run. And that's really bad, as you might imagine. I think we published a blog post about how we do this a couple of months ago. So on Amazon, etcd requires quorum-based decisions to make retain its consistency, which means you essentially need an odd number of nodes. We don't really want to have 3, so we run across 3 availability zones. 3 isn't very many. That doesn't give us much margin for error. Specifically, we wanted the ability to lose an availability zone and also have one server down for maintenance potentially at the same time. And the minimum number you can do to do that is 9 etcd servers. So you have 3 in each availability zone. Thankfully, that is just about within the recommended number. That's like the maximum recommended number of servers. And we run these as individual auto-scaling groups on Amazon. So we essentially have 9 auto-scaling groups of 1. And that means that they're all individually numbered. And we have an application that runs on that when it comes up that reattaches the correct EBS volume. So that means we can actually terminate all 9 of our etcd cluster, all the nodes completely, and within 2 minutes we have a whole new cluster which has retained all of the data. If we lose under the quorum 4 of them, then we have no downtime whatsoever. And crucially, while that is down, the only real limitation is Kubernetes can't make scheduling decisions. So if your applications crashed at that point, or specifically if the nodes crashed and went away, your workloads wouldn't be redistributed. So that's like an aside on how we run that. However, the nice thing if you're building applications is all of that is squished down into one lovely abstraction layer where we just run our applications on Kubernetes. And most people in the company don't really need to know how all of the underlying stuff works in order to do their job. And you also get nice things like dashboards, so you can go and see what your application's running. So in our case, we are taking Go and Docker and Kubernetes, and that gives us like a really, really nice way to run our applications. I mentioned Go is going to statically link all of our libraries into the actual binary, and that means we don't need a runtime. We can run our Go binaries in a Scratch container with no shell, which makes it a bit more secure. And then we can run those really easily on Kubernetes, and Kubernetes will deal with resource constraints and node failure and moving all of that So we can pretty much just ship lots of services on top of Kubernetes. I've bandied this word around quite a lot, though, which is a service. And in our case, we're talking about an individual Go binary that's essentially a HTTP server. And it might have a number of handlers, so a number of different paths, but ultimately it's listening on a port, receiving HTTP requests, and responding with those. These are going to communicate in some way, so usually over some form of transport. And originally we used, a very long time ago, we used RabbitMQ to build a really quick prototype. However, that doesn't give us all the kind of things that we wanted. So ultimately we need many copies of each service to provide reliability and scalability. And we need some way of communicating between these. And crucially, if you're communicating between lots of services, there are a number of things you need to look for. So lots of stuff, which I won't read through. But ultimately, you need to know where they are. You need to be able to tolerate failure. And because we've built a cloud-native application, these services are coming and going. So we need some way of routing requests reliably through a series of services that may or may not be there when we try and make the request. And our services I mentioned are small Go binaries. We could build lots of our own code to do this. If you're using Java or Scala, you could use Finagle, for example, which does most of that list. However, we want to keep our services as small as possible and as simple as possible. So we just want to use HTTP at this point, and that means we need some way of routing these requests. And Kubernetes gives us a concept called a service, which allows you to route requests to multiple copies of a receiving service. However, of this list, that only gives you the top 2. So that leaves us in a bit of a quandary. So in our case, we've chosen to use Linkerd, which is one of these kind of service mesh products, which I guess is the marketing term for them these days. So if you have seen Linkerd, great. If not, there's Envoy, Istio, and a couple of other products which are going to do these kind of things. And all this is going to do is take a request and then decide where to route it to. So in our case, we proxy to the local Linkerd, and our service here is completely unaware of how it is routed to its destination. We then are using Kubernetes Service Discovery to get that information so we can locate where all the copies are. Linkerd has a namer that will connect to this and do that for you. And then as a result, it will route the request to the instance it most likely thinks is going to serve that correctly. So we'll do things like retries if it can't connect, or if it's an idempotent request. It load balances across all of these. And if there is a failing one, it will take that out of service and then work out when it's back in service and then start routing traffic back over to it. So to go, again, back to the top, in our structure, we have an ELB at the top, load balancer on Amazon. Our traffic then goes into an edge proxy, which is something that we've written, which again is a really simple Go HTTP server. This will then route to another service. So we call this tier like our API services, and these are going to do things like unmarshal JSON and decide what to do with that request. And the cool thing is that, as an example, we have a public API that you can use if you're a customer. And we route this particular /webhooks on our top-level API to this particular service. And what that means is we don't need to redeploy our edge proxy every time we increase or change our API. If we want to add a new endpoint, we just deploy a new one of these APIs, which makes it almost riskless. We're running our services in Kubernetes. They're resource constrained, so they can't consume all the CPU and memory on the machines. If you deploy a new one, no requests are going to it. So we can deploy new features on our API with nearly zero risk, which, if you're building something that stores everyone's money, is really important. Beyond that, we then route to a number of other requests, a number of other services. So in this case, we're actually deciding what you're doing with your webhook. We'll authorize you, and then we will probably put it into the database to register a new webhook handler. And that then means when you go and use your card in a shop, we'll actually ping your webhook in real time. Quite often you'll get that before the receipt prints, but I don't want to guarantee that. Yeah, so this is like a really basic flow through that. Each one of these arrows is obviously a massive abstraction because we're actually putting this thing into Linkerd. It's deciding which service to route it to. It's then routing it to that. And Linkerd itself is communicating over an overlay network, which you are required to use if you're using Kubernetes. So there are many, many, many layers of abstraction here. But ultimately, if you're building like business domain level logic, it's an arrow. So it's really nice and simple. And then behind this, we have some databases and maybe other providers. So we use Cassandra for almost all of our data for reasons I'll happily chat about. And then other things like Kafka for replicated logs and asynchronous communication. So that kind of gives you an overview of how we've gone taking really basic Go HTTP servers. We're deploying those into Kubernetes. We're deploying quite a lot of them, but they're all relatively simple. And as a result, we can put together all of the features that you kind of would expect of a bank. We can store, we have a ledger which can store all of the transactions on your account. We have integrations with MasterCard, faster payments, direct debits, chaps. All of those things are literally clusters of small Go servers that are running within this. Because we haven't built our load balancing into those servers, we can actually, and we pulled that out, we can deploy service in any language. We just need kind of a common contract. So if you're deploying a container that listens on a HTTP interface and can serve requests in a specific format, then we can deploy those into our infrastructure. So a number of our data science applications are in Python because there's much better libraries for that than Go. We have to integrate with IBM MQ for a number of things. So we don't want to use the Go bindings for that because we'd have to shell out to, well, we'd have to use the C bindings, which is really horrible and complex. So instead, we can just write a Scala service that does this for us, and we can use the Java bindings. Same with a load of SOAP servers. If you're building financial products, you've probably had to integrate with lots of financial companies. That SOAP is the pinnacle of technical achievement. Nothing will surpass SOAP. And Go's XML support isn't that great, so we use Java services for that. But ultimately, these just kind of end up in Kubernetes and kind of business as usual. So there's a number of things that we've kind of learned off the back of that. One of them is that we need to constrain our complexity. So we build lots of small services, and we've pulled that complexity outside. So if we have problems, we can go and look at the code base of that particular service, and it's really short. So that's nice and easy. The other reasons that we've done this kind of, taking this kind of approach is security. So if you're deploying one service of 400, you don't have to give everybody access to deploy that service. You can deploy them within Kubernetes using network isolation and role-based access control so that specific people can only see specific secrets, they can only deploy specific applications, and those applications can only even establish TCP connections to other specific services. So that isolation is something Kubernetes gives us, which is a massive benefit for us. The other one, strangely, is like operational ease. So while we do have an incredibly complex system, if you're building a day-to-day product, you can quickly create a new service. You can commit that. We go through our change control process, which is primarily GitHub, and then you can build and deploy that into Kubernetes. And the kind of feedback cycle on that is potentially minutes. We have a number of staging environments. You can deploy things really quickly into those. When you are deploying them into production, there's loads of readiness checks that will ensure your service is correct before the traffic's rolled over. So those things are like of kind of crucial importance. So those are the reasons kind of why we've done that. I guess there are also a load of things we've learned over the last year or two. So one of them, which I guess is a little bit, I've kind of touched on it, is that we want to make our services as small as possible. So we have quite a lot of services that are quite tiny compared to a lot of like big companies. So using Netflix's approach, for example, most of theirs will run like an application on a server, and they'll run many of them because they're massive. And in our case, we don't have that kind of scale. So we're running lots of applications on the same server, but they are constrained. However, if we're doing lots of things in the same binary, then it's sometimes hard to establish what the performance of that thing is. It's harder to look if you're looking at graphs of overall performance of a service, and this particular thing is slow. If that service is doing many things, then that's difficult. If you're reading many things off a queue, for example, and it's doing different logic within that same service, even though it's very similar logic, potentially you'll be stalling the queue if one of those executes incorrectly. And we've had lots of examples of that. Keeping them really small also means that thankfully we can do that because Go has really low overheads. So I mentioned our default provision for a service is, I think, 30 meg of memory, limited to 100 meg of memory, which is insanely small. We can use Kubernetes pod auto-scaling to scale that out horizontally. And then we'll tweak those based on the performance characteristics of the service, but ultimately keeping them really small means it's very flexible. One thing which I wasn't really sure of right at the beginning was now we prefer services over shared code and libraries. So if you're building something that would be a library, you could compile that into many services. The problem is if, for example, you have built something that is in 200 of those services and you now need to fix a bug, you now have to deploy 200 services, which is really bad. So in most cases, we pull that kind of library code into a service itself, and we'll just make calls to that. And that means we only have one place where we have to fix that. If we have to change the interface, yes, we still have the same problem. But again, it allows us to constrain that kind of complexity into a small place. Also, I guess this applies to all large code bases. Sometimes there's a way to do things that is already there, and there is a better way to do things. And if you're in a really large code base with a development team that is scaling, often it is better to do it more consistently than have many different ways that are slowly, progressively better if you're doing the same thing in many different places. And this is something that, we've kind of had to learn, I guess, over time. Sometimes if you have so many services, you'll be unaware that there is a service that already does the job you're building a service for. So we've had to make sure that we share these things around and get better at communication in that regard. When we're doing designs, we share internal RFCs of what we're going to do to solicit feedback across the company. And that again allows people to point out that, hang on, we've solved this problem, it's over there. So that's kind of a problem with all large code bases. In this case, they're discrete applications, so sometimes the visibility on that is lower. Also, quite often you'll be using shared infrastructure. So I mentioned that we use Cassandra to store our data. If you're using one Cassandra cluster with many, many key spaces, and you have one service that thrashes Cassandra, then you're going to create a knock-on effect for a number of other services. So there are a few options for that. If you have large enough scale, you can segregate those into many clusters. If you don't, then that is quite expensive. Some products you can run at much smaller volumes without dedicated servers. So for example, we run Kafka as a number of stateful sets within Kubernetes, rather than running a number of massive dedicated Kafka instances. And that means that we've isolated performance problems to those clusters individually. And that allows us to have better performance overall and higher uptime. Also, I mentioned complexity is huge, so onboarding people is hard. But again, that's something that I think building your application as a series of microservices and using a language such as Go has made that problem a lot easier for us. So people can join our company. They have a really simple language to learn, but the framework is almost non-existent. We don't have loads of code you need to learn. So you can pretty much start working on a specific service. The deployment is super straightforward, so you can get up to speed really quickly and then slowly learn all the other things around the company. So that's something that we've focused on quite a lot over the last year or so. But ultimately, we still need to reduce our complexity hugely. And we do that by isolating those things. I mentioned we use IBM MQ for a couple of things. We have to because we integrate with other third parties. But we don't want all of our other services to be aware of that. So we can encapsulate that complexity behind a service and then have a kind of more normal interface into our infrastructure. And finally, I guess we need to monitor everything. So if you have hundreds of discrete services, monitoring and health checks and being aware of performance is probably the most important thing. So yeah, I think if we're going to ask what we do differently, a long time ago we would have probably done things hugely differently. We have learned that our abstractions across services were often incorrect, and we've had to change those quite a lot. So knowing more about your domain is kind of quite important. And then breaking those things down into smaller and smaller chunks has worked really well for us. And yeah, that's it. Thank you very much. Does anyone have any questions? Yes.
So you mentioned that services should be as small as possible, so that everyone's got an idea of the scale that we're talking. Can you, without obviously divulging company secrets, can you give an indication of what a small service would be?
Yeah, so I mean, we're super transparent as a company. Some of the services are big, but by big I mean like thousands of lines of code, not tens of thousands of lines of code. They will have potentially 12 plus handlers that are all doing different things but loosely related, and for us that is quite complex. So some of them will be really small, like 100 lines of code, a couple of hundred lines, 1 or 2 handlers, that kind of thing.
How difficult or easy is debugging?
That is a very good question. How hard is debugging?
Yeah.
Really hard. So I guess there's a couple of different areas where debugging is quite hard. Debugging Go itself is relatively straightforward. There's loads of really awesome tools if you're debugging an individual binary. So this is really very much a question of how hard is it to debug Go applications versus how hard is it to debug distributed applications. And the answer is Go, really easy. Loads of really cool tools you can use. It has runtime tracing. There's a thing called pprof, which you can use to literally trace execution, so you can see where all the bottlenecks are. And you can trace the Go routines as well. So you can take like a sample of execution from the runtime, and you can actually pull that into some tools and see, like, you can trace where the execution went. So that's amazing. Debugging distributed applications is really, really hard. And we use a number of tools for that, and we have a number of our own internal tools. Ultimately, we're debugging those problems in production because they're things that have happened. We're trying to work out why they've happened, or at least what triggered them, so that we can then reproduce them locally and fix them. Using things like tracing, like Zipkin. So I'd say probably distributed tracing is one of the most important tools for infrastructures like this. We tag every request at our API or various edge points with unique request ID, which is then passed through between every service. So like when a service makes an ongoing HTTP call, it has a context because Go doesn't have thread local variables, so we have to pass a context object through every method call, which pros and cons of that, a bit tiresome. But ultimately, we have this request ID that we can then take out of this context, serialize as a header, send that to the next service, which then deserializes it and puts it into the context and passes it on. The context also allows us to pass things like deadlines and allows us to cancel contexts. So if something is errored much further up, we can actually cancel child requests through that infrastructure, which is quite cool. But yeah, that's hard, and I'd say like instrumenting applications using distributed tracing, and we also log every log line with that request ID, so we can pull all the log lines for a specific request, even though it might have touched like 40 services across 40 different servers. We can pull that together and see the logs for that request. That's quite important.
You have like you said, you have like 400 services, and knowledge sharing is a big piece of.
Yeah.
Do you have like an inventory of services that your developers will go through, or they have to just remember?
That's a good question. We don't have a special place. We actually use a monorepo. So there's like one gigantic repository that you clone down, which has every service literally as a folder. within that. But yes, that is difficult if you are new to the code base, because memorizing quickly what all 400 of them do is impossible. Whereas if you've been around for a bit longer, you kind of have, that's like innate knowledge that you've soaked up over time. So no, we don't have an explicit tool that does that. It'd be really cool if we did. And yeah, we have a list of these, and they all have a README that kind of, I guess, hopefully is up to date, but probably not. But that defines at least what the service is intended to do. So you have some idea of that. And then, yeah, it's really just communication between teams to like help onboard people and get them up to speed. Yeah.
How have you gone about handling longer running process flow related things? Obviously, it's very easy to think about. Yeah, this service does this quite discrete thing. It's all very stateless. But have you had the need to tackle some of the long running orchestration of issues?
Yeah. So we have a number of longer running orchestration things. So some of them, strangely, are actually integrating with other payment networks, as an example, where you send, some of these networks are not request response, and you will get the response at some arbitrary amount of time. And that means that we had to architect that in such a way that we send the thing and it's kind of complete, but we need to check it later to confirm that it didn't fail or needs to be resent. And then at some point we will receive a response, and that is essentially a new request which processes it. And then when we come back around to check it, if it's already complete, we can just drop that, like retry on the floor. Longer term ones, some of the more interesting ones are things like when you sign up in our app, there are many stages. And ultimately, someone may just put their phone down partway through that. So those are kind of modeled as state machines, and we have specific services that orchestrate those state change, like state transitions. So they will use lots of other services to do specific chunks of that work, but there'll be one service that kind of controls the overall state transition. So we have a few like that. Some of the other ones, sometimes they have a really long request, and it would be nice if we didn't do that, or we'll trigger it, and then we'll have something that's on a queue that will poll periodically to check when it's been completed, or time it out if it's taken too long. So we use Kafka to defer a lot of those things. Yeah, so a combination of all the above, I guess. Yeah.
Just be curious about your dev experience. Do developers spin up their own cluster locally within services?
Yeah. So we have a really basic tool that will spin all of them up. And actually for local development, most of us use a Mac, and we can compile the binaries locally. So we run all of the shared infrastructure using Docker Compose. So we can run Docker containers for all of our databases, queues, etc. And then we'll spin up a subset of like the services that you're running on. That's like really not ideal. We have not cracked how to do that well. Ultimately, if you're not running one of the services, you'll get a timeout at some point which will tell you that it timed out hitting that service. You're like, okay, I need to go and start that one. And we have a few scripts that can identify those code paths. So yeah, if I was developing locally, for example, on a specific area, I would fire up a subset of the services and try and run on that. Running 400 binaries on even a reasonably powered computer is moderately difficult and doesn't work particularly well. And that's something that we still need to solve. So whether we solve that by running machines in Amazon, we might use Minikube for it. So you run Kubernetes locally, but I don't think that... Pardon?
The new Docker tools for Mac have the Kubernetes engine.
Yeah, they just added that, haven't they? So that gives you tools to easily spin things up, but again, running that number of things on your computer is quite difficult. So yeah, that's something we still need to solve. One option is we push those into like custom staging environments and allow you to easily like modify a service locally and route traffic down in and out of Amazon effectively.
A few questions.
Yep.
One is like having like 400 services, does it not add latency to your calls?
Yeah, so that's a good question. Yes, it does, inevitably. However, that is a kind of surmountable problem, and I'd say that the advantages of the speed that you can develop things and deploy things is really what we're aiming for, not necessarily the overall speed of the API. So card networks are a good example of this. Card networks are really slow because they've been around from the 70s and there's no real incentive to make them faster. If you tap your card and 5 seconds later it works, that's okay. So what that means in practice is we will get an API, well, we'll receive a message, we'll move the money in your account, and we'll send you a push notification, and often that will beat the card network to your phone. That doesn't do it all the time, or if we have some kind of problem which means that we put all those things through several queues, which means that we've isolated your card definitely working from getting a push notification, which actually we had some problems with the last couple of days if anyone was watching our status page. But what that means is we've isolated the extremely reliable components from things that don't have to be as reliable. And yes, making lots and lots of network calls definitely does increase latency, but it's something that you can reduce quite significantly by, Linkerd is maintaining connections to everything, so you don't have the cost of opening a new connection and sending a request. You've already got an open TCP connection. You can make your services moderately quick, so like that latency should be like well under a millisecond between services. However, that is one specific problem that we had with Go and Kubernetes. If anyone's used or is aware of like how the Linux scheduler works, it does time slicing on CPU, and Kubernetes, if you're using C groups to throttle CPU on a particular process, and you use all of the available CPU in your time slice, you can't execute, you're just paused until that time slice ends. And the default on Linux is 100 milliseconds, and the default in Kubernetes, which is not modifiable, is 100 milliseconds. So we've had to modify, we have a fork of Kubernetes that we've modified that in, which allows us to configure the time slice window, and changing that to like 5 milliseconds or 2.5 milliseconds increased our latency by like an order of magnitude. Decreased our latency by about an order of magnitude. So those are, yeah, it does increase latency, and it's something you need to like instrument and be very aware of. But yeah, you can make really fast API calls.
The other one is like, as Monzo is relatively new in the market,
yep.
You've already got 400 services, microservices. So do you see that going to like 1,000 services?
The graph is like nearly exponential, unfortunately, which is probably, which is similar to the rate that we're hiring new people as well. So yes, it's something that we have to be quite aware of, but we've deliberately put the infrastructure in place that would support that. So it's really a question of can we, as a company, maintain that level of like knowledge. But it's just the same as having one really big application that had loads of like classes. It's just that those classes are different processes running on different machines. So trade-off. Anyone else? Cool. Thank you very much.